And so to question 14. Right, this really threw a lot of people. The paper got quite hard at this point, I think, for many people. It's asking you to combine a standard nickel and iodine half cell. In other words, this one and this one. Okay. You have to realise that one of these has got to be oxidation and one of them has got to be reduction. You don't get one without the other. So many people put nickel 2+ with iodine and ended up with iodide and nickel, which you can have a positive side and negative side. It just doesn't make any sense. One of them has to be flipped. You've got to work out which one's got to be flipped. The one that's going to go in the forward direction, in other words, going to be reduced, is the one with the most positive reduction potential. Okay, for the species that's going to be reduced. And so iodine must be being reduced and therefore must react with the nickel. Nickel's got a more negative reduction potential, so that one's going to be flipped. And you should be writing this with state symbols, but there we are. I'm not going to worry. For now, that should be straightforward, but it clearly wasn't. Right, so that you then have to predict, giving a reason, the direction of movement electrons when you combined nickel and manganese half cells. And I think it was about a kind of 50-50 what was happening there. So the answer is the electrons go from Mn to the nickel half cell. We'll look at the numbers in a second, and I'm going to give you what it says in the mark scheme to start with. So you needed to be really precise with your answer here to get the second mark. Okay, this is the sort of thing we need to practice, I think. So the reduction potential of, or for the reduction of nickel 2+ is greater than, you've got to be clear when you're comparing two things, than the E standard, or the reduction potential for the reduction of nickel, manganese 2+. Okay, so nickel 2+ going to nickel has a more positive value than Mn2+ going to Mn. Right. There's other ways of answering it. You could simply say that nickel 2+ is a stronger oxidizing agent, which we practice quite a lot of that kind of thing, than Mn2+, or Mn is a stronger reducing agent than Ni. Either of those are okay. Sorry about the writing there. And you can just look at your tables for the data points. Okay. Calculate the cell potential. Well, hang on. So just because that happens, so the nickel is therefore being reduced, so electrons must be travelling to the nickel electrode to give to nickel 2+ ions. That's what's going on. That's why it's from manganese to nickel, if that wasn't clear. Right, so we first established which was going to be reduced, nickel 2+, and then it must be the nickel electrode that then has the electrons that's able to reduce these ions in solution. Right, calculate the cell potential in volts when a standard iodine and manganese half cells are connected. Okay, so what's that equation then? What's that equation? Which one are we going to use? The reduction potential, or the E standard for the one that's reduced, take away the E standard for the one that's oxidized. I just double checked that so I didn't make a Charlie of myself. And that makes sense, doesn't it? Because this is going in the forward direction, the reduction is going in the forward direction, which matches how it is in the table, and the other one is the oxidation. So you've got to work out what's going on with the numbers. So the value for the well, I should go to the back over here. So the one that's reduced is the one that's got the more positive E standard, so 0.54, and the one that's oxidized, we'll be looking at manganese, and the one that's this one is the one that's going to be are going to go in the oxidation. So this is going to be ox. This is going to be red. Or if you prefer, working out which is going to be the left hand side and the right hand side electrode. As you know, you write it as, if you're writing drawing the full voltaic cell, we draw the oxidation on the left, so left hand side, right hand side. You can do it that way if you prefer. And we go back over here. The values for the reduction are plus 0.54, and the value for the oxidation is minus 1.18. So over here, plus 0.54 minus 0.18, and that comes to plus 1.72 volts. And if you've connected it properly, you should never get a negative one. A few people gave negative values there, and of course it couldn't be if it's set up properly. If you wrote it out as E right hand side, take away E left hand side, it's exactly the same sum, it's exactly the same answer. The next question was to work out the best reducing agent. So let's go back over here. We did a few of these in class. The things that are reducing agents are the things that are oxidized, and here are the things that are oxidized, right? Mn goes to Mn2+, nickel goes to nickel 2+, or iodide goes to iodine. It has to be one of those. And because it's being oxidized, it's going in the reverse direction. So which one's best to go in the reverse direction? Well, it's the one with the most negative E standard, so it had to be Mn, so I'll put Mn over there. Nearly everybody got that wrong, so you do need to practice a few more of those. Question 14e, state and explain. It definitely needs a bit of a polish, this question, I think it's fair to say. So many of us got the first part, but didn't quite explain it well enough. So let's make sure we get that right. So the positive electrode in concentrated aqueous sodium chloride. So just remind you, in solution we've got sodium ions, hydrogen ions, chloride ions and hydroxyl ions. So at the positive electrode, you're either going to oxidize chloride or hydroxide to get chlorine or oxygen. And you should know from the lesson that we did this and practiced it, and most of you did actually, you generate chlorine if it's high concentration, and that's from the reaction. You can write it out like this, or you can do half stoichiometries, whatever, half the coefficient. So one lot of chloride goes to half chlorine plus one electron. Either of those is okay. And all you had to mention for the explanation was that chloride is oxidized as it's in high concentration. That was enough for the mark, actually. And it's all to do with Le Chatelier's principle. If you crank up the concentration of the chloride, it kind of pushes this equilibrium to the right and forces, kind of changes the reduction potential, the oxidation potential of that, if you like, pushes it in that direction. At the negative electrode, you've got a choice of either hydrogen being produced or sodium. So first of all, I'd ask you just to plug your brains in a little bit. It was never going to be sodium, was it? Because you can't produce sodium in water, because it's going to react immediately and form hydrogen. So it must be hydrogen that's produced. And you've done this enough times at GCSE to know that it's hydrogen produced. And you could get away with simply writing 2H plus 2E goes to H2. It allows that, but it really prefers, as I've told you enough times, water. This is straight from the data book, you don't have to memorize this. Plus 2 electrons goes to H2 plus 2 hydroxide, and that's our explanation for why the pH increases in these circumstances. But the explanation was I thought difficult to get right from the mark scheme. You had to simply say that the water or the hydrogen ions were reduced because the Na plus is a weaker oxidizing agent, or simply say that sodium cannot be reduced to sodium in water, or simply say that it's easier to reduce H plus than sodium ions, or H is lower in the activity series than Na. Any of those would have done, and some explanations you gave me were satisfactory, but you needed to explain that a little bit better. Many of you didn't do a comparison. And it is a comparison, isn't it? It's comparing the ability to reduce sodium ions, or essentially hydrogen ions. Okay, well, let's finish this off. Then let's do question 15 as well. So vanadium, this just about everyone got right. So you can't see very well on the page, but this was V2O5, which is +5. This was VO2 plus, which is +4. So 1 electron difference between them, and nearly everybody got that. Okay, so then you were given the load of electropotentials for various vanadium species. Now these questions are not super easy, nor are they impossible. Have any of you got them right? Okay, so the first one, something that can reduce VO2 plus to V3 plus, but no further. So let's find that one. So VO2 plus to V plus. So it's this one here. So something that can reduce this stuff. Okay, something that can force that to go ahead, but no further. And here are our options. So it's a non-vanadium species. These are the non-vanadium ones. So it's going to be something from in there. So in other words, when you combine the E standard for, or the reduction potential for VO2 plus with minus the value for the reduction potential for the species here, then and that's going to be positive, but not so positive it's going to push it further. So let's go through a few examples. So let's start at the bottom and work our way up. If you did plus 0.34, take away plus 1.36 or plus 0.8 volts, you're going to get a negative value for each cell. So it's going to be that. So it has to be something above it. So let's have a look at this one to start with. So this is the reducing agent. So we're to combine plus 0.34, take away, because it's going the other direction, isn't it? Because it's oxidation, minus, take away 0.17. That'll give you plus 0.17. So that reaction can go, the reaction using H2SO3, and that's a perfectly good answer. It's also true that lead can do it, because if you did plus 0.34, take away minus 0.13, that would be a positive value. So lead can do it. Whoops, that's not lead. Lead can do it too, and zinc can also reduce it. But zinc, having a very negative reduction potential, will also reduce V3 plus to V2 plus. Okay, if you just plug in the numbers, it'll make sense. So there we go, that's what I was drawing. So they're the two possible answers. Zinc will take it too far. So in other words, the higher up the list, the more powerful the reducing agent. You've got to decide how far up with this you need to go. Something that could reduce it all the way, well, I've already covered that. The thing that's the most powerful reducing agent is zinc. That can take it all the way to V2 plus, and many of you got that right. Formulate an equation for the reaction between VO2 plus and, this is a tricky question, vanadium VO2 plus and vanadium 2 plus to form V3 plus. These are two half equations, treat them as such. So VO2 plus going to V3 plus and V2 plus going to V3 plus. Well, that one's easy. This one you can balance it yourselves, but it's on the left hand side of the page. We can balance it ourselves, shall we? One oxygen, 2 hydrogen ions, and this side is now 1, 2, 3 plus 3. What have I done wrong? 1, 2, 3, 4, and this is plus 3, so we need an electron here, and then just balance them just by cancelling the electrons. So you've got 2H plus VO2 plus V2 plus goes to 2 V3 plus. I'll write it over here just for completeness. So 2H plus VO2 plus V2 plus goes to 2 V3 plus. Sorry, I've squeezed that in there. I'm now just going to check I've got that right. Oh, I've missed out water. There we are. I'm going to squeeze in water. Water was there, but I forgot to copy it across. That's that one. And then comment on the spontaneity of this reaction. So let's finish this off then. and we need to work out first of all the E cell. We've got, this is our reduction, this is our oxidation. Look up the values. So the VO2 plus going to V3 plus to start with is here. So it's what I'm writing, E red, take away E ox, minus 0. Whoa, let's get this right. Just realised what I was doing wrong. I was looking at the wrong number. So the reduction is the top one. I just looked at the wrong number over here. So for the reduction, it's VO2 plus going to V3 plus. It's plus 0.34. Plus 0.34. Take away the one for the reduction, which is minus 0.26. That comes to plus 0.60 volts. You get a mark for that, and then delta G is equal to minus N Fe. We know that value. Let's think about how many electrons are transferred here, and lots of us struggled with the number of electrons transferred for some reason. We've gone from VO2 plus to V3 plus. It's a 1 electron change, and V2 plus to V3 plus 1 electron change. There's a 1 electron transferred, so N is equal to 1. Let's just get rid of that because N is equal to 1. All you got to do then to get delta G is times Faraday's constant, which is 96,500 times by, it's not 96,500, what is it? 9.65. Yes, that's right. Times 0.6, and that comes to minus 57,900 joules per mole. We want to do it in kilojoules per mole. Not that it really matters. Either would be okay. But look, it does say comment on the spontaneity, so you have to say that it's a negative delta G, so it is spontaneous. That's how you get the third mark. And that's it. All done.